In our last lecture, we were discussing about the methods of riser design. And so we had discussed about this Caines method. And in this method, we were we were calculating two different parameters. One was freezing ratio and other was your volume ratio. So freezing ratio is basically the ratio of the cooling characteristics of casting to the cooling characteristic of your riser, and cooling characteristic is the ratio of surface area to the volume of casting or of your riser, and your freezing ratio should be greater than 1 for proper supply of molten metal from the riser in order to compensate the shrinkage defects. And in that particular you can say the method, we were calculating the different freezing ratio and correspondingly we were obtaining the volume ratio. And in Caines method, initially they gave us empirical based curve, and from that curve we can predict the volume ratio, and from that volume ratio, that is the ratio of your riser to the volume of your casting, and then your casting volume is already given to you. So if you have this volume ratio, then you can easily calculate the volume of your riser. And later on they modified their graph, or you can say their expression of freezing ratio in terms of material constant and that volume ratio, and then the same method can be utilized in order to obtain the volume ratio of different materials. And after that, now I'm discussing the drawbacks of this Caines method. And in this Caines method, we were using different material constant like A, B, and C, and which keeps on changing. So it's a very difficult job to remember these material constants. And also there are different materials of which these material constants have not been obtained. So there are different methods to calculate these material constant, and it is a very challenging task. Then second drawback is the calculation of freezing ratio. So this calculation of freezing ratio is complex, and mostly in the case of casting which has a complex geometry. So there the surface area calculation is very difficult job. So this was the second drawback. And third drawback was that you were calculating the freezing ratio from the ratio of cooling characteristics, and then you were also calculating the freezing ratio from that expression, which is equals to x is equals to this a upon y minus b plus c. And then by equating these two expressions, you were calculating a polynomial equation, and then by trial and error method, you were calculating the diameter of your riser, and therefore this method is tedious. And after this, there is another method of designing the riser for successful casting and defectless casting, which is the modulus method. So in modulus method, this Chorinov rule is basically utilized, and this rule gives you an idea that the solidification time of casting is related to the volume to surface area ratio. So this expression we have already studied in our previous lecture, that time period of solidification is equals to the C into V by A whole to the power n, where Cm is your mole constant, V is the volume of your casting, and A is surface area of the casting, and n is the exponent. So in general, we consider this n is equal to 2, and however its value changes between 1.5 to 2. So the same formula, you can say solidification time period formula for the casting, can also be applied for the riser. And here the term which is volume by area is termed as the modulus, or in other words, it is also known as the solidification modulus. So if this modulus is high, then the solidification time period is also more. For a successful riser, the modulus of your riser should be greater than the modulus of your casting. So this Chorinov rule indicates that the casting with higher modulus, you can say volume to surface area ratio, will cool and solidify more slowly than one with the lower ratio. That means the time period of solidification of riser must exceed the time period of your main casting in order to supply the molten metal till the end, and in order to compensate this solidification shrinkages. So Chorino further suggested that the riser must be designed with higher modulus than that of the casting, and how much it should be more, it should be greater than the modulus of your casting. So he empirically obtained that modulus of the riser should be equal to at least 1.2 times the modulus of your casting, where MR is the modulus of the riser and MC is the modulus of the casting. And risers are of two or three types. The first riser is the top riser. The top riser is that riser which is directly placed over the mold cavity and which can directly supply the molten metal during the solidification shrinkage. However, the other type is the side riser, which is conventionally, which we have already seen in our most of the figures of your casting, that the riser is placed at one end or one side of the mold cavity. Now the question arises that what should be the optimum size of your riser in case of the top riser or in case of the side riser. As we know that the surface area of the riser is a very governing factor which determines the solidification rate of the material inside the riser. So surface area controls the solidification time period, and in order to maximize this time period you need to minimize the surface area. First of all, the first thing you have to do is to calculate the surface area of your riser. In case of top riser, if you consider that the riser is of cylindrical in shape, then you can say the top side and the side is in contact with the mold cavity. However, the bottom side is in contact with the mold cavity through which the material is supplying into the mold cavity, and all three sides, you can say the curved side and the top side will have a direct contact with the mold cavity. However, the bottom side is not in contact with the mold cavity, rather than it is in contact with the mold material supplied into the mold cavity. Here the surface area the surface area of the bottom surface will not participate in the surface area calculation. However, in the case of a side riser, all of the surfaces, including the top surface, bottom surface, and the curved surface, it will participate in the heat transfer. So now you have to calculate the area, and then you can minimize this area by the partial differentiation. You can say differentiation is used to calculate the diameter, and then we have seen that in case of the side riser, the relation between the height and the diameter comes out to be h by d equals to 1, and in case of the top riser this comes out to be 0.5. This is already given in the books. If you refer the books, standard books of production technology, there you will see that what should be the optimal design of the riser, and for that in case of cylindrical riser, what should be the final outcome in terms of the relationship between the height and the diameter of the riser. So if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.